Alright, I've had to change my plans here because I'm at my house. I don't have a whiteboard here, so I'm going to lecture using this notepad as my whiteboard. And you won't be able to see me, but you can see my hand and I'll be writing. So we're going to start about talking about black holes. Okay? But to understand what a black hole is and how it could affect us and how it could destroy life on Earth, we first have to understand how this came about. And we have to go back to the late 1800s. Back in the late 1800s, there was a guy named Albert Einstein. And one of the things that was happening in physics around that time is they realized that the idea set down by Isaac Newton in the 1600s of how everything moved, the mechanics, kind of fell apart when you started getting close to the speed of light. There were problems, and nobody had resolved those problems. And there were other people working on it. And they had a different approach. The idea was that knowledge has to get transmitted by some kind of wave or particle, and that there's a limit to how fast that goes, and that limit is the speed of light. And so some of the physicists at the time were trying to prove this by saying, well, can we prove that the speed of light is a limit? And Einstein came at it in a totally different way. He said, no, let's not do it that way. Instead, let's just assume that the speed of light is constant in all reference frame. And if we assume that, what does that imply? And if the implications are true, then the assumption had to be true. So it's kind of a backwards way of working, but that's what he did. So the assumption is that you assume the speed of light, remember speed of light is c, is equal to c in all reference frames. I know these are kind of technical terms you probably haven't heard of before, but I'm going to explain. So, for example, if you were traveling on a train or a truck, or whatever you want to call it, and if you're traveling on the truck and you throw a baseball in front of you, okay, while the truck is moving. So you throw the baseball at like 60 miles per hour, and the truck is going at 60 miles per hour. Then to somebody standing on the side of the street up here, they would actually see the baseball coming at you, coming at them at 120 miles per hour. Because you get the speed that the guy throws it, plus the speed of the truck. Now the difference is when you get close to the speed of light, that doesn't work. Let's say instead of throwing a baseball, he has a flashlight. And he turns on the flashlight. How fast does the light go away from the flashlight? Well, the light travels at the speed of light. Now let's say he's riding on top of this truck, but this truck's amazing. It's going 0.99 times the speed of light. When it does that, do these add together? The answer is no. To this person, the light coming to him is still only going the speed of light. You can't add those together because you can't get greater than the speed of light. The speed of light is an absolute limit. That causes problems in the way we think of the mechanics of the world. So, one of the experiments that they did, and it was an interesting idea, is let's say we have a bottomless pit. And we have two people on the sides of this bottomless pit, right here, and they're playing catch with a ball. They're throwing a ball back and forth. Okay, we know that if you throw it at a certain velocity, and the distance is here, that the time that it takes is equal to the velocity. So you just do the velocity times the time is equal to distance. Everybody knows that. If you're going 50 miles per hour and you go for 2 hours, you go 100 miles. So you take your speed times the time and then equals the distance it goes, right? Okay, so let's say the distance across here is just d. Now this was the same thing. What if instead of using a ball, they use a flashlight? And so they shine a flashlight across here. When it hits here, this person also shines a flashlight back directly, or it's kind of like a mirror bouncing back and forth. So the speed of light is just bouncing back and forth between the two. Now instead of v, this becomes c, because c is the speed of light times t, that gives you your distance. perfect sense. This works fine under Newtonian mechanics. But what if, while you were doing this back and forth, both of the people jumped into the bottomless pit? So as they're falling downward, like this, you shine the flashlight across to the other one. But by the time the light gets across to the other one, that person isn't there anymore. They have fallen because they're falling downward. So the light actually makes a path that makes a curve. So that makes a curved path. Okay? So then that comes back, it makes a curved path back. That path is longer than the distance d. D is this distance right here, but the curved path has to be longer than that. Just the same way a hypotenuse has to be longer than the leg of a triangle. So if this is longer than this, and I look up here, my distance got longer, but c can't change. So to keep this the same, time becomes a variable. I know this is really crazy, but that's what really happens. So, this is the way Albert Einstein looked at it different than everybody else. And he generated what he called his special theory of relativity. And the idea was, and the idea that was so different, is everybody up until that point thought that time was an absolute. That 1 second is 1 second everywhere in the universe. And time doesn't ever change. And Einstein said, no, that's not the case. The speed of light is constant everywhere in the universe. Time becomes a variable. So, under special relativity, you can create something called the gamma factor, which is 1 over the square root of 1 minus v squared over c squared, where v is your speed, c is the speed of light. The closer you get to the speed of light, the bigger this value becomes. Okay? If you're going exactly the speed of light, then this would become 1, and 1 minus 1 is 0, and 1 over 0 is actually infinity, which can't ever happen. So anything with mass, any mass at all, any particles, cannot actually go the speed of light. They can get really close, but they can't go the speed of light. So he realized that if you are going super fast, special relativity occurs for when your velocity is close to the speed of light. Then 3 things change. Your time is slowed relative to someone else. Or relative to somebody moving at a different reference frame. 2, your mass increases. And 3, your length in the direction of travel shrinks. You're like, what? It's kind of weird, but if you have a truck standing still that is this long, right here, this is my truck, if it's going close to the speed of light, v is approximately the speed of light, it'll get shrunk in the direction of travel, and that same truck will look like this. Same truck, but now it is a smaller distance. Okay? How much this changes is determined by the gamma factor. So the time is slowed by amount equal to gamma. The mass increases by a factor equal to gamma, and your length and direction of travel shrinks by a factor equal to gamma. That's where the gamma comes in. So the closer you get to the speed of light, gamma gets bigger, the more these effects occur. That is what causes special relativity to occur. You're like, is this true? Yes, we know for a fact this is true. In fact, Einstein's theory of relativity was the most tested physics theory in all of the 20th century, all the 1900s, and it never once failed. Not once. So we know this is the fact. This is just the way the universe works. You're like, well, what's this have to do with black holes? Well, the black holes, he said, okay, let's expand special relativity to the case where we have what he called general relativity. So special relativity was the case when you're traveling close to the speed of light. But general relativity, on the other hand, was more general. He said, no, this occurs whenever you have a highly accelerated reference frame. Okay, that's a complicated way of saying wherever an object, if you let go of it, gets accelerated quickly. Well, that's what gravity is. Gravity is just acceleration. If I drop something, it accelerates to the ground until it hits it. Okay, so a highly accelerated reference frame we usually think of as places where there's a lot of gravity. So a highly accelerated reference frame, all these effects occur. Same effects that occur in special relativity will occur when you have a highly accelerated reference frame. Not only that, he said that mass, which we usually think of as attracting objects, that's how Newton thought of gravity, as two masses attract objects together. Okay? Let me check this real quick. Okay. He said, no, mass isn't, the property of mass doesn't make things attract together. Gravity is actually that mass warps space. And by warping space, it changes the path of objects so that they want to come together. It's just a different way of looking at things, but it has huge implications. All right, and we'll do that in the next video. So this was part 1.